This is Ian Barnes, and this is my Lab 2 projectile motion. So the purpose of this lab was to compare the position of a projectile affected by gravity and air resistance computationally and experimentally. So my object of choice was a cue ball, which has a mass of 0.16 kilograms, and for my experimental model I used tracker, my computational model I used GlowScript. So the principles of this lab were the position update formula, which is position final equals position initial plus velocity average times delta t, and velocity final equals velocity initial times plus the net force divided by m times delta t. And we can use these in the GlowScript for iteration to after each delta t, it will update the velocity and position. And to get the net force, we use two different forces, the force of gravity and the drag force, which is just negative mg, and then negative b, which is a constant, times the magnitude of v times the unit vector of v. And for the lab procedure was to capture a video of the cue ball being thrown as a projectile, and then import that video into Tracker application to track the position of the cue ball on a frame-to-frame time period by using the center of mass, and then go over to GlowScript to create a computational model of the same cue ball being thrown for t seconds with only gravity acting on it, and then do another computational model where you add drag force and manipulate the constant b to change the output of the code to try and get it as close as you can to the experimental model. And then after you do that, plot the data generated of both the computational outcomes and the experiment outcome on a graph and compare the outcomes of the experiment. So in my experiment, you can see in the bottom left me throwing the cue ball and my data to the right of it. And you can see that the delta t is 0.0333 seconds, and my initial position is 0.0079 in the x component and 1.063 in the y component. And then to get the initial velocity, I did position final minus position initial over 2, and I got 1.20 in the x component and 1.66 in the y component. And I divided by that 2. And then in my computational analysis, you can see I have my initial position on line 49, and then right under that I have my initial velocity to just like initialize the GlowScript model. And then I have my delta t right under it, and then I also have g, which is 9.8, which is constant, and then my drag force constant, which I manipulated in my second computational model. And then on line 79, you can see I have my net force, which is the gravitational force, plus the drag force. And I didn't add the drag force in the first model, it was only the gravitational model. So yeah, and then I have the iteration below. And then once I graphed all of these, you can see that my experiment and my gravity and air resistance model are very close, very similar, but my gravity is not very similar, just because it's not very realistic. There is air resistance, and in the second computational model it accounts for that, making it like the gravity not being as strong. And then position tracker, sources of air was the position tracker. The center of mass wasn't perfect every time, like it's not the true position of the ball, because I mean it's just me clicking. And then rounding errors with initial velocity and initial position weren't exact, because there was really no true measure unless we had like an actual like speed tracker of the cue ball at the beginning. I mean, that equation is not as accurate as it seems. And then the mass of the cue ball was not exact. I never weighed out the cue ball, I just looked it up on the internet. So yeah. And then additional questions, with terminal velocity, in the gravity only model, there's not a terminal velocity because of the constant acceleration down. But in the drag model, velocity is on the right in that graph. It isn't reached because the ball hits the ground before it can reach the terminal velocity, because as you can see, it starts to like level out. But we could drop it from a higher height to get a true terminal velocity with the computational model of gravity plus drag, because it would have more time to reach that terminal velocity. And then for the second question, if the ball was thrown straight up, would it take longer for the cue ball to hit the ground than the regular experiment? And I would say yes, because it would spend extra time going straight up and then stopping to go back down rather than being thrown at an angle like in the experiment. And also you can use the kinematics equation and see that the initial velocity in the y component would be smaller than the original experiment than in this if it was just thrown straight up. And yes, and thank you. That is it.